All right, it says Mrs. Curtis was eating M&Ms. Of course I was. And wondered if her bag really had the distribution of colors that M&M says should be there. So here's our data. I've made a list of all the colors that M&M offers. And then what I saw. This is what I observed. Like, this really happened. This is data. Okay, right here in this column. I observed 14 blues, 12 oranges, 8 greens, so on, so on. Apparently there were a total of 106 M&Ms in my bag. And then right here, this reported by M&M, this is like the claim. This is what I would expect to see if M&M is a nice, truthful company. I should see 10% blues, 10% oranges, 10% greens, and so on. So we're going to be comparing these things in Chapter 26. You'll notice this is different than what we saw back when we studied proportions. In proportions, we might consider just one category, like the percent that are brown. But in this one, I need to consider all those percents. And I'll just tell you what, this is not how we're going to do our null. That the proportion of browns is 30%. And that the proportion of reds is 20%. And that the proportion of yellows, I'm going backwards, is 20%. I mean, and like you would have to keep going. That sounds horrible and awful, and we're not going to do it that way. Instead, we're going to learn a new kind of test. There's multiple proportions here, multiple proportions. So new kind of test is in order. That test is called chi-square. This right here, I like to write it this way. Little loopy x, which is actually the Greek letter chi. No, that is not chi, that is chi, chi. It's a new family of distributions. Just like the T, it changed shape a little bit. The chi will change shape. We'll take a look at that in class. It is skewed to the right. This is, whoa, that's very different. Chi-square looks like this. It's like, poof, okay? Really different. And again, it changes as the degrees of freedom change. So this picture will look slightly different depending on the degrees of freedom. Important for you to know that this inference we're going to do is only for categorical data. Really important. So important I wrote it twice. Really important. And in addition, we're only doing hypothesis tests for chi-square. There will be no confidence intervals. There will actually be 3 kinds of tests. One of them we're going to talk about today is called goodness of fit. Looks kind of like the word golf. We'll also study homogeneity. And the one that I teach my intro class is independence. So 3 kinds of tests you'll observe in 3 different videos. All right, so let's take a look at, in general, some things you'll need to know about hypothesis tests when it comes to chi-square. Step 1, we're still going to be writing hypotheses, just like always. But this is different. Writing it in English will actually be easier in this chapter than trying to do symbols. Symbols would get kind of yucky. Step 2, just like always, we're going to check conditions. You're probably not surprised to see this first condition, random. The data should be a random sample. That's a recurring theme for us. And then sample size. When we did proportions way back in Chapter 20, it was like we check the NP and the NQ. So that's a similar condition here. We're going to expect 5 per cell. And we'll look at an example. Don't panic. Step 3 is our mechanics. Just like we had a formula for a t-score or a z-score, we have our formula for our chi-square score. Like here it is. Ms. Curtis, this looks like giant math gibberish. Yeah, it probably does, but I'll show you how to use it. We're going to take our observes minus our expecteds. We're going to square that, divide by the expected. And this thing right here just means we're going to add together. Again, we'll practice this. Step 4 is our conclusion. Just like always, we're going to have a p-value. We're going to compare that p-value to some alpha level. We're going to reject or fail to reject. And we're going to be sure that we actually answer the question in context. All right, so pretty much the same setup, but a few changes. So let's see how that works. Step 1, we're going to write hypotheses. So null hypothesis, status quo. Nothing strange is going on. That means I might say The distribution of candy is what M&M claims it to be. Notice I didn't have to say that the proportion of brown was 30%, the proportion of yellow was 20%. I just say, yep, we get the same percents that M&M says we're going to get. Alternative, you probably can imagine it's going to sound like the opposite. The distribution of candy is not what M&M claims it to be. So this is my M&M company, you are a bunch of liars. Okay, that would be my alternative. I don't think they're telling the truth when they give me those percentage breakdowns. So notice I've written these in English. No math symbols, English. All right, step 2, we check our conditions. Now, this first one, this really is more of a mental condition. You don't have to write it down, but you should confirm that we have categorical data. We cannot do this chi-square test without categorical data. So you'll notice it's getting harder and harder to tell them apart. We're learning a lot of different tests in this class. So recognizing categorical data is one way to help yourself know, oh, maybe a chi-square is a choice. All right, so condition number 1, we're verifying that we have a random sample. I didn't give you really any information about the bag of M&Ms, so I actually think it might be more accurate to say that I have a representative bag. Representative. Meaning, I don't think my bag is anything special. You know, like I bought it at Walmart. No big deal. It's the same as any other bag of M&Ms I'd find anywhere. And then condition number 2, I need to verify that the expected counts are greater than 5 in each cell. So we're going to figure out how to verify that. All right. Remember, there were 106 M&Ms. So if 10% of them were blue, well, then I take 10%, I multiply that by the 106 M&Ms, and that means I should have seen 10.6 blue M&Ms in my bag. Now, I know a couple of you are like, but Miss Curtis, you can't get 10.6. You can either get 10 or you can get 11. Like, I know it's an average, okay? Think of the expected as being like an average. Maybe if I got lots and lots of bags, it would average out to 10.6 blue M&Ms in every bag of 106 M&Ms. All right, so again, to find orange, I take that 10% and multiply it by 106. So the expected count for orange is 10.6. All right, I'll do just a couple more. Again, 10% times 106. Miss Curious, like we know by now, it's definitely 10.6. And the next one, 0.2 times 106. I got 21.2. So at this point, you should pause the video and just fill in those last two numbers, because make sure you can multiply to get percentages. Multiply percentages. So as you might imagine, the numbers are just going to get larger. So the condition is met. These expected counts are all greater than 5. So that's our check, it works. But notice I had to actually do some work here. That's kind of like if you have to make a histogram. Like you have to show your work. You can't just say, oh, I think they're all bigger than 5. Actually, work it out, okay? Work it out. Okay, so our conditions are met. I'm going to be performing what's called a chi-square goodness of fit test. You must know this name. It's called goodness of fit because I'm seeing how good this fits my data, these percentages. I don't know if that'll help you remember. All right, so then we move on to step 3, which is the mechanics. So notice if you did not fill in your chart, there's the rest of the expected counts. I actually need my observed and my expected numbers to calculate chi-square. So one more time, here was that formula for calculating chi-square. My apologies, I should write that sigma really big. So remember, this symbol just stands for adding things together. All right, so I'm going to go ahead and do an example for you, okay, right here. I'm going to look at the blues. formula says I take the observed number. That's 14. I actually saw 14 blue M&Ms. I'm going to subtract 10.6. That was my expected number of blue M&Ms. The formula says I square it. That's right here. And then I divide it by the expected, 10.6. Right, that's my piece. Then I can plug that in my calculator. It's going to be a number. Gosh, I'll go ahead and do this one. Make sure that you use the parentheses just as I have them printed. So I got 1.09. All right, so I'm going to show you another one, and then you should be checking to see, can you work these out? So, gosh, I wish I had an orange marker to do the orange one. I'll do this in red. So I'm going to take my observed number, subtract my expected number, square that, and divide it by the expected. And again, you just plug that in your calculator. So I'm going to do one more so you can, again, try to get the hang of this. Green, I'll put it over here in green. It's my observed minus my expected, squared, divided by my expected. And again, like I just get a number for each one of these. I would repeat this formula for every single cell, okay, or every row there. So by the time I'm done, I have 6 different numbers. You should pause and work those out. All right, so I went ahead and worked them out. Notice I have 6 different pieces, formulas here. So I have 1, 2, 3, 4, 5, and my last one's hiding down here, 6. All right, 6 different ones, one for every color. And for my chi-square, I would actually just add these together. Like that's the final step. So our chi-square is actually the sum of all those pieces, and I got 9.31. So that's how we calculate chi-square. This is what's called our test statistic. This thing is equivalent to a z-score or a t-score. It's our chi-square score. All right, so in order to calculate a p-value, we're going to need to know the degrees of freedom. Degrees of freedom is the number of cells minus 1. It's not n minus 1. This is very different. I had 6 different colors. So for my degrees of freedom, I would take 6 different colors minus 1. That gives me 5. 5 degrees of freedom. All right, be sure, pause, rewatch, go back. This is definitely a very different kind of hypothesis test. In order to find my p-value, I'm going to come to my calculator. I'm going to go to distributions. And just like we had a normal CDF, we had a t-CDF, there's also a chi-square CDF. Pretty cool. Chi-square, since it is that left skew, we always go to positive values. So I would type in my test statistic, 9.31, comma. Let's see if I can jump back here for just a moment, show you what I mean by positive values. Draw a little picture here. So chi-square looks like this. It's very skewed. So our 9.31, I don't know, is maybe like right here. And we always shade up. With such a large value, 9.31, chi-square is on a very different scale. So instead of calling this really far away out here 99, I'm actually going to use 999. Okay, I'm going to go really big. So that's my comma 999. And then, as you might expect, we need to include the degrees of freedom, just like we did for the t problems. And that's my p-value, 0.097. All right, so the last step would be to make a conclusion. So I'm going to take that p-value, and you'll notice how similar this is to what we've done in the past. Our p-value is 0.097. That's higher than alpha. I forgot to specify an alpha, so I just put it in here that alpha is going to be 0.05. Right here. That means I failed to reject the null hypothesis. It's bigger. That means there is no evidence that the distribution of M&M colors is different than advertised. Different than advertised, that was my alternative hypothesis. So I've got no evidence that it's different. That means, oh, I can't sue M&M Company. even though mine didn't exactly match up, I had more than 10% of blue M&Ms. Let's kind of jump back to these observed versus expected. I had more blue, I had more orange, I had less green, I had more yellow, I had more red, I had much less brown. But this is saying I don't have evidence that it's different. I just happen to get a slightly different mix. I can't go sue the company for false advertising. If you have a TI 84 Plus Silver like me, you might want to watch the extra video that shows you how to do one of these by hand on the calculator.